Okay, so this is called gluing, gluing and homotopy canonicity. So I need to tell you what I mean by gluing. Sorry. And I'm going to start. This talk is going to have sort of two parts. So the first part, I'm going to tell you about 3 different ways to think about gluing. And then in the second part, I'm going to say something about how to use gluing to prove homotopy canonicity and what homotopy canonicity is and what it has to do with gluing. So, there's sort of 2 older perspectives on what I'm calling gluing, and only one of them is called gluing. The other one is called logical relations. So I'm going to tell you about these 2 things and how they're related to each other. And I'm sure that for part of the audience, one of them will seem familiar and the other one will seem bizarre. And for the other part of the audience, the other one will seem familiar and the first one will seem bizarre. So for me, it was a revelation when I learned that logical relations were actually this familiar thing called gluing that I knew and loved. But then yesterday I was trying to tell Christina about it, and she was like, "Why do you reformulate logical relations in this weird way?" In a way, this is the whole point of this program, is that we have people coming from different backgrounds, and we can put together different things. So to sort of motivate what's going on, suppose you have some type theory, and we want to prove some sort of canonicity result, like every term of type natural number or Boolean, maybe S is a bad word, T of type nat is equal to some numeral, so some number of successors applied to the 0. And I'm putting equals and equals to in quotes because it will mean different things by it as we go on. But suppose you want to prove some statement of this form. How do you go about it? Well, if you're a type theorist, then you sort of naturally want to do things in some sort of type-directed way. And of course, I'm going to sort of try to be a type theorist here and repeat some things that I learned from people like Bob Harper, and probably I'm going to say things that are completely wrong. But I'm trying to give you some idea, give the homotopy theorist some idea of how a type theorist might think about these things. So you want to prove something about nat, but this term might involve lots of other types. So we can't just prove something about nat. We have to prove something about all types. So this property of being equal to some numeral, we've got to generalize that to some property that can be stated about all types. So this is the, oops. This is the logical relations point of view. So first we have to generalize to a property and I'll call it something like R sub A of terms of type A for all types A. And this property is sometimes called things like reducibility. It's sort of intuitively supposed to express that the term which satisfies this property is well behaved in some way, like this, a term of type not is well behaved if it reduces to a numeral. A term of a function type is going to be well behaved if it takes well behaved things to well behaved things, and some sort of various other generalizations of this. And then you can sort of do induction over the construction of types in order to define this. And then in order to prove that it always holds. So we define R of A inductively on the construction of the type A out of type formers, and then we prove that R of A holds of all terms inductively again. And maybe these 2 steps get mixed up in some fancier type theories where we have universes and things like that. There are various different ways to make this more complicated. And so then in particular, you conclude that R of A of T, or R sub nat of T holds. And then because you defined R of nat to be this thing which you wanted, then you get the desired conclusion. And there's some other generalization that has to happen too when you sort of have to prove this not just for closed terms. So this was some statement about closed terms in the empty context. But you have to sort of generalize this to a statement about open terms, including variables as well, in order for the induction to go through, because when we construct closed terms, we may use open terms and so on. OK. So this is the type theorist's point of view. Did I get it mostly right? OK, great. So here's the category theorist's point of view. The category theorist says, well, I like to use universal properties. So I'd like to have some object with a universal property that I've built out of the type theory, and then I can conclude this from using that universal property. So there is an object which has a universal property which is canonically built out of the type theory, which is the syntactic category, or the classifying category, or category of contexts, or whatever you want to call it. So this is a category whose objects are contexts in the type theory, and whose morphisms are substitutions or telescopes of terms, or lists of terms. I like to think about the objects of this category as just being types. And if you have nice, well-behaved dependent sums, then that is good enough. And in general, doing it for types will sort of tell you how to do things for context. And this thing has a nice property that it is initial object in some category of structured categories. So whatever sort of structure our type theory has, dependent products, dependent sums, identity types, universes, whatever, we build, there's some that can be expressed as structure on a category, or maybe a contextual category, or a category with families, or all these sort of different ways to express the structure. And we build the category of those things, and then the syntactic category is the initial object. This is sort of how the semantics of type theory in all sorts of other categories works, because we have something like maybe simplicial sets or some higher topos or something like this. We build an object in this category of categories out of that thing, and then we have a map from the syntactic category into that other category, and that tells us how to interpret all of the constructions in type theory as being constructions in this other world. Okay? So now we can also use this universal property to prove this sort of statement. And this argument is, we'll see that it's sort of a reformulation of this, and writing it in this language, I think, is due to Peter Fried. So what do we want to do? We want to prove something about terms of type nat in C, but we also want to relate it to natural numbers in the world of sets, or whatever meta theory we're working in. Right? So this n is some external natural number outside of the type theory. So what we want to do, we're going to have to use the initial property, the initial algebra object property, to map out of C into some other object of this category. And this other object has to be built out of C, because we're going to have to conclude something about C. And it also has to be built out of sets, or whatever higher groupoids, or whatever the meta theory is, in order to say something about the external natural numbers. So the question is, how can we build an object of this category out of C, and I'll just say set for now. So there are various constructions that we can do in these categories of structured categories. The one that turns out to be, so for instance, there's some sort of trivial things we could do. We could take the product of C and set. But that wouldn't really be very interesting, because it wouldn't sort of tell us how they relate to each other. It would just sort of take them completely unrelatedly. So the construction which turns out to be really useful is the comma category, or gluing construction. So to define this, suppose I have a functor from between two categories, then I can consider the comma category. So this is a standard construction in category theory. This is the objects, this is D over the functor H. So in general, for a comma category, you would have two functors. You would have one functor with a different domain over another functor, but here I'm just taking the identity functor. So an object of this category here is an object D in the category D together with an object C in the category C, and a morphism from D to H of C. Okay, so if H were the identity functor, then this would just be the category of arrows in the category C, and in general, it's this other thing. And a morphism in here is just a pair of morphisms in D and in C, which makes some square commute. And the really nice thing about this construction is that if C and D are structured in some way, and H is nice in some weak way, which I mean, you can make this precise in various general ways, which I'm not going to, then this comma category has the same structure. So by structure, they might be toposes, or they might be locally Cartesian closed. They might be categories of contextual categories with various other things. But the important thing is that H doesn't have to preserve all of that structure. You might guess that, that you would want H to preserve all of that structure. And that's enough, but it turns out that that's not necessary. So for instance, for example, if C and D are toposes, you might think, well, H should be a morphism of toposes. It could be either a logical functor, or it could be some part of a geometric morphism. But actually, in the case of toposes, it turns out to be enough for H just to be left exact, to preserve finite limits. And then you can do this comma category, and you'll get another topos. As long as C and D are toposes, and H preserves finite limits. So it doesn't have to preserve any of the other structure.
You mean elementary topos, I guess?
Yeah, elementary topos.
Of course, this is true for grossing topos too, but you're interested in the case where C and D.
Yeah, I mean, it's. I think it's actually not true in general that if C and D are Grothendieck toposes, then this is also a Grothendieck topos. You might have to assume this is accessible or something.
I think for CCCs, it was just positive.
Possibly, yeah. Probably for LCCCs, you needed to preserve finite limits. Yeah. More generally, if C and D are algebras for some two monad, then this can be a lax morphism for that two monad, and then you have various other things like this.
Did you say something about the origin of the word gluing?
Yes, in fact, that was what I was going to say next. All right. So this categorically, this is a comma category, and it's called gluing because it has a geometric interpretation as well. Why gluing? This is sort of a, well, I'll put it there. Why gluing? So if in the case of, sort of the simplest case, I think, to understand of this is if C and D are sheaf toposes. So suppose C is sheaves on some space U, and I hope I get this the right way around, and D is sheaves on some space K. Then it turns out that this comma category is sheaves on some space X, where X is the I don't know how to write this. X is the disjoint union of U and K as a set. So the topology on X is going to be different from this disjoint union, but as a set, X is the disjoint union of U and K, and U in X is an open subspace, and K in X is a closed subspace. Is that right? Did I get the right way around? Yeah.
So what is H?
H is what tells you what X is. Right. So in general, there could be many different spaces with these properties, that it's the disjoint union of an open subspace that is U and a closed subspace that is K, so that depending on how the boundaries stick together. And I could put them completely disjointly, or I could put this part of U on this part of K, or this part of U on the other part of K. And H is precisely what tells you the information about how to put them together.
How to glue.
How to glue, exactly.
So if you want to glue an open, I don't know, a knife fold along its boundary, along the boundary, you need that. You
Right.
need
Gluing data, or whatever you want to call it. Yeah. So this is why we call it gluing. But this perspective is maybe useful in some cases, but for the canonicity sort of results, I don't think it's particularly useful, as far as I know. But yeah, I mean, in some way you can, I mean, and the construction that I'm going to give you can be thought of in this way, sort of. Although the syntactic category is not sheaves on a space. But you can sort of think about it as if it were sheaves on some funny kind of space.
So you say the topology on X is determined by this?
The topology on X is determined by knowing that U is an open subspace of it, K is a closed subspace, it's the disjoint union as a set, and the data of the functor H, from sheaves on U to sheaves on K. And conversely, doing a topology on X with these properties determines the functor H. Twice more. This is not really obvious, but it's kind of cool, I think. So
Functor turns out to be composition of direct image and recursion.
yeah, in one direction or the other. I guess maybe probably the only direction that makes sense. OK. So right. So canonicity. What do? We want to put together C and set. And so there's an obvious functor from C to set, which is the global sections functor. So if I have a type or a context A, that maps it to the Hom set from the terminal object into A. Terminal object is the empty context. So if A is a closed type, this is just the set of closed terms of type A. So this functor H sort of incorporates information about closed terms, which is a good thing because that's what we want to get out. And it sort of obviously preserves finite limits because it's a Hom functor. And it doesn't preserve all the structure, but it's going to preserve enough structure sort of to be nice in order to make this gluing work. And that's actually going to be and this necessity for H to be nice is what's going to come back to bite us later when we try to do the Homotopy version of this. But just in the simple case, now we can perform this gluing construction. So we have this glued category set over H, and so C, being the initial object in this category, has a map into set over H. And we can say more about this map because there's a forgetful functor from this glued category to C itself. So which just picks out the object C in C. So D, comma C, comma phi maps down to C. And this forgetful functor is actually also a structured functor. So it preserves all of the structure of whatever categories we're looking at. And that essentially follows from the construction of this structure here. Well, when in the second part of the talk, when I talk about how to do this in the case we're interested in, hopefully I'll get a chance to say a little bit about how this works. But basically, the way you build this structure is you do it on C, and then you sort of lift it to D along these maps.
So in this case, set is sheaves on the point.
Right. And so we're gluing, if you think about, if you thought about C as sheaves on some space, then we're gluing that space with a point in some way where that space is ending up open and the point is ending up closed.
So you're constructing a cone.
We're still constructing a cone. And for that reason, this category here is sometimes called the Sierpinski cone on C. Because it's sort of a cone using the Sierpinski topological space rather than the unit interval.
And C sits there as the open part of the cone.
Right.
And the point is the closed point.
The clone point is a closed point. Yeah. So if you did this to sheaves on a space, on an actual space, I think what you would get is sheaves on a space with one point added, where that point is closed, and all its open neighborhoods are just the extension of open neighborhoods of the original space, including that adding that point.
And this structure functor, which the functor projection down preserve is
Restriction.
restriction
Right.
of the sheaf on the whole cone to the open part.
Right. Thanks. So all of this happens for any structured category C, and we could think about the sheaves on a space or whatever. This part only happens when C is the initial object, is the syntactic category, because that we use the fact that it's initial to get this structured functor. Right. In general, there may be no sort of way to extend which preserves all the structure. Yeah. There will be functors in the other direction, like direct image or whatever, but they're different.
Set being included in the cone,
Right.
the open set is a subtopos.
Right.
So the sheaves in there sits in the big topos. So this projection down has
An adjoint.
a right adjoint.
Yeah. Yeah. But that right adjoint is not in general this. Right. The right adjoint doesn't preserve all the structure. The right adjoint is a sort of the direct image of a geometric morphism, so it preserves limits, but it doesn't preserve exponentials and power objects and the things which these structured functors have to preserve. Yes?
May I also say, so if we forget about this analogy for a moment, so what it says that for every object of C, this function we should build from initiality, that for any object of C there is a canonical subset of
You're jumping ahead.
morphisms from one. I'm just reading of your
Well, I didn't tell you what this composition is yet.
Oh, okay, you did.
Right? But the point, as Vladimir is jumping ahead to say, is that this composition is a structured functor from C to itself. And since C is the initial object in the category of structured functors, there's only the identity morphism there. So this is also structured, and therefore it is the identity. So
So you wanted to say that
I was going to say that it meant that in C, for every object, there is a distinguished set of maps from one to this object,
right.
which is preserved by all the morphisms of C.
Right. So this
Kind of a canonical global section.
this functor, which I may as well call R,
which is smaller than global sections, or
which takes an object C and maps it to a triple consisting of a set RC. So this is a set because it's an object of D here, and an object of C, which has to be C, this little object C itself, because this is the identity. And then a function from RC into H of little c. So what this functor R does is it equips every object of our category C with a set together with a morphism, a function, into the set of global sections. So we have a family. We can think of this as a predicate on the set of global sections, although in general it might have multiple witnesses of truth for a given thing.
A priori, it's not clear that this is not just an isomorphism, right? That this map is just not just a projection a priori.
Yeah, I mean, it might just be an isomorphism.
Yeah.
Probably it is, no?
In many cases, it is.
But in some cases, it's not.
Yeah.
But that would create a subfunctor from the functor of global sections.
Yeah, right.
Well, it's not necessarily monomorphic either, actually.
Oh, right.
Yeah. But it gives us some functor to set, which maps to the set of global sections. Right? So, in other words, we have C, which maps to set in this way, and then here's the global sections functor, or the set, right in this syntactic category, this is the set of closed terms, and then there's this natural transformation here, which maps this set into the global sections.
If R is left exact or whatever, you could iterate this construction.
Yeah, you could.
Maybe it's closed or
I don't know. Has anybody ever tried that? In a little bit, I'll say something which might have something to do with that. I'm not sure whether it will or not, but give me a minute. So hopefully the notation should sort of make clear what's going on, right? So R sub A of t here is sort of the fiber of this map over the term t. So if this is an injection, then the fiber is either empty or inhabited, and that's just telling you whether or not this predicate holds. And in general, we're doing something a little more general where we might have multiple witnesses of this relation. Yes.
some functor are structure and other are not. So for instance, global section is not.
Right.
And R itself.
R itself as a functor is also not structured.
Not structured.
Yeah, it's only, sorry, R as a functor to set is not structured. It's only structured as a functor into the gluing, the scone, the gluing category. So, which is a manifestation of the fact that the other forgetful functor from this glued category into D is not structured. It preserves like finite limits and stuff. It's like one of these left to right inverse direct images, but it's not. It doesn't preserve all the structure. What? R will not preserve exponentials, not as a functor into set. It does, of course, as a functor into here. Okay. So now we've categorically done up to step 2 of the logical relations, and so now what happens to step 3? It turns out that step 3 is really easy because R is a functor. So step 3, if I have suppose I have a global section of a type A, so this is right, a closed term of type A, then I have R, this functor into the glued category maps this thing to a commutative square. It looks like this. Right? So 1 maps to this guy. A maps to this guy. Right? So these are all sets. This is a commutative square of sets. And now H of 1 is just 1, and R of 1 is just 1 because this functor R preserves all the structure. So in particular, it preserves the terminal object. Right? So it takes this terminal object to this terminal object. And now this function here, right, HA is just Hom from 1 into A. And so this function here just picks out the term T itself as an element of Hom 1A. And so the fact that this square commutes means that there is some element of R of A living in the fiber over T, which is precisely to say that R sub A of T holds. We have a witness of it. Right. And it's even sort of naturally split surjective, I think. It's always a surjection is the conclusion.
I see. So it's not.
And in many cases, and in all of the small cases, it turns out to be an isomorphism, I think. So for instance, in the case when A is nat, right, you have to make sure that what is the structure. In order to get that out, we have to say what is the structure that gives us the natural numbers object. So the natural numbers object in the glued category is the ordinary set of natural numbers mapping into the global sections of the type of natural numbers where we send n to the corresponding numeral. And so in particular, that means that we get this definition of RA of T for A being nat as what we wanted it to be. It holds precisely when something is a numeral. It comes from an external natural number. And in this case, this map is in fact an isomorphism because different natural numbers give different numerals. Right.
Why do we get n?
N is, you mean N is set on the left-hand side?
Yeah, so this
Where did this come from?
is the set of natural numbers.
Yeah, but why is it?
It's,
This is the type of natural numbers as an object of the category, the syntactic category.
that's R of little n. Okay.
R of nat
Okay.
is the set of natural numbers.
Was R defined, or was R some arbitrary structure?
R is defined by the fact that C is the initial object in the category of structured categories. So that means that it has to map the natural numbers object of C, namely nat, to the natural numbers object in the glued category, which is this. I mean, I haven't proven that, but it's true. Right. Right. So that goes into the proof of this statement. That sort of whatever structure these guys have, this guy has the same structure that you get by putting together those two structures. Right. So nat is the natural numbers object of C. N is the natural numbers object of set. And so we put them together, and we get the natural numbers object of the glued category.
Yeah, but
This has to be proven. Yeah.
independently.
Right.
Because this won't be true, for example, for real numbers or something
Right.
like that.
Well, yeah.
Or,
Yeah.
so you have to check that this object has the universal property. It's sort of the initial, etc. That's the way you prove.
Yeah. So you have to check that that this guy inherits all of the structure, sort of piece by piece,
But
and that.
it's not sort of pairwise. I mean, it inherits all the structure, but it's not clear that, let's say, the real numbers in there sits as pair of real numbers.
Right. So it's what's always true is that this forgetful functor to C is always preserves the structure. So whatever structure you're doing, the thing that sits here will always be the thing that you had in C, but the thing that sits here will in general be some more complicated thing that you've built out of everything else.
Yeah.
So for the real numbers, you should expect to have the real numbers object here, but not the set of real numbers here.
Yeah, because on the right we have a countable set.
Yeah. It's
Yeah.
the real numbers.
Right.
It's a countable set of real numbers.
Yeah, I don't know. I'm not going to make any claims about what the real numbers are going to be, but.
But that's well defined, almost well defined question.
Yeah. Okay. Yes.
So you get canonicity, but you don't get the ability
Right. Not obviously. So you I mean, you have to sort of beta reduce the proof a whole lot in order to extract an algorithm.
Standard problem with logical relations. You get an algorithm if you kind of have an algorithm map down.
Mhm.
It was in type theory.
Okay.
It's a nice bit of a theory.
I think the algorithm is hidden in the proof of the fact that it's natural numbers on the left-hand side of that arrow.
And evaluation, I mean, everything.
Because a priori it can be absolutely anything. So when you prove that it's actually natural numbers, that's when you create the algorithm, I suspect.
I think the algorithm is actually hidden in everything, because you also need to know how you build the structure here that might go into these terms, and you have to know how you build this structured functor by induction over the construction of C. So the proof that C is the initial object also sort of involves an algorithm that gets into the act. So
The proof that it's n on the left-hand side really just talks about the natural numbers, whereas the algorithm has to depend on all the other types of terms this one has
right,
as well.
right.
They particularly use evaluation.
Mhm.
It's kind of
Yeah.
separating
Yeah.
the proof into two big pieces. Or
Mhm.
a big piece and a small.
Right.
A big
Right.
piece.
So rather than one huge induction,
Yeah.
like that the logic of relations is, that sort of the categorical proof compartmentalizes it into, there's a proof that C is the initial object in this category, and then there's a proof that for each type constructor this inherits the corresponding structure, and then for the natural numbers is a particular case of that, and then you put it all together.
It's really fancy way it inherits it, because for example, for the function type, what's on the left is not the same as
Right.
Yeah.
It is fancy, and it's a little.
But how can but there's something funny here. You say it's always have to be surjection,
Yeah.
Yeah.
but
The right-hand side is countable. So
the right-hand side is countable. So what you get on the left-hand side is something. What is by definition is the left-hand side?
I mean, I didn't tell you. I mean, it involves knowing how the structure is built.
the exponential of natural numbers with natural numbers can be constructed explicitly in there.
Mm-hmm.
I mean, since the natural numbers are explicitly there,
Mm-hmm.
and exponentiation is explicit too,
Mm-hmm.
one should be able to construct explicitly the exponential
Yeah.
and check what's happening.
I think in the case of the exponential, you'll get again a bijection.
No, it can't, because
Why not?
one is countable. Well,
Well, I mean, the thing on the left is not the exponential.
Not the exponential, but something weird.
It's the functions which are tracked by some code.
Exactly.
Which are tracked by a term.
Right. Or it functions together with the term that tracks them. Yeah. The place where you get something that the place that I have in mind where you get something that's not a bijection is with the universe. When you take A to be the universe, then R of A is not just the closed types, but the closed types together with a predicate on them, and on their closed terms. Hopefully I'll get to say a little bit about that later when we talk about univalence and why that sort of classifies the small types. Yeah?
So I just realized, in the version here, are you just looking at where H is global sections, or it's global sections up to?
Well, so I was kind of vague about this. I mean, so this, I was describing the classical version here, where this is literally global sections, and we get out this sort of literal computation sort of thing. And then if I have time to talk about homotopy canonicity, then we'll do a case where this is sort of global sections modulo homotopy in some way, so we can change equals to homotopic to. Okay. Okay. So now, so that was two ways to think about gluing, and now I want to tell you about a third way to think about gluing, which I just realized a couple weeks ago. And which expresses it as the same sort of construction which we've been using in homotopy type theory to calculate homotopy groups and characterize path spaces of higher inductive types. So let's sort of forget briefly about gluing and think about this method, which Dan has pioneered it. Dan Licata and Guillaume other people have been using. So here the idea is we have a type, say W, which is sort of initial in some world. It's got some universal property from mapping out of it. And maybe we have some point x naught that lives in W. And we want to know, we want to understand the type of, or maybe I have 2 points, say, W. And I want to understand the type of paths or equalities in W from x0 to y0 for 2 points of W. So for instance, maybe I want to characterize the fundamental group of the circle, or the loop space of the circle, or the higher homotopy groups, or some more generalization. And then what we observe is, well, we can't do much about this because x0 and y0 are fixed. So instead, we can sort of generalize and try to understand paths from x0 to y for all points y in W. And now this is a family of types over W, a fibration over W, and what we can do is we can define some other fibration and prove that it's equivalent to this one using the inductive property of W. So what we do is we define a fibration of codes from W, which is some dependent type on W. And we can do this by induction on W because W has a universal property. W is a higher inductive type of some sort. And now what we want to do is we want to show that for every y, codes of y is equivalent to paths from x0 to y. So these are sort of codes for paths. They're sort of, you can think about them as canonical forms of paths of some sort. And so then we can define the two functions in either direction. We have a decode function that says given any y and any code over y, I can give you a path that codes for. And again, this can be by induction on W because I have something that does for all y in W, so I can use the induction principle. And we also define an encode function that goes the other way, which is usually easy. So this, for any y and any path from x0 to y, I get a code. And this one we can just define by taking the identity path, or to take, I need some element of codes of x0, and then I transport along paths to give you this. And then you can consider the composites. And then we prove that decode following encode and encode following decode are identities. So, and then there are various sort of refinements of this where we could consider truncating the paths or do some higher paths, or maybe doing only part of these and getting out partial information and something of this sort.
That's another way to construct the path space.
So yeah, this is a general way to characterize the loop space of something. So in the case of the circle, what this is what Dan Licata made out of my original proof of pi1 of the circle. Here we take the codes fibration is that of the universal cover that's defined in a concrete way. We say if W is this circle, then we define a fibration over the circle by induction on the circle. So we give the fiber over the base point to be the integers, and then we make it the helix by putting things together as we go around the loop. And then we write the decode and encode and check that they're identities. And again, sort of one of these is easy, and the other one can be done by induction on W. And then we get, as a particular case, the thing that we wanted to know, that the paths from x0 to y0 are equivalent to codes over the particular point y0. So in the case when x0 is also y0, we get the loop space is the codes over the chosen base point.
Why do you call it code and decode bubble?
There are a lot of things that you could call it. You want to say anything about? I mean, like I said, these are like canonical forms for paths. So
I see.
they're like in the case of the circle, the codes over the base point are integers. I can regard an integer as a code for the path which goes around the circle that many times.
So it's somehow you want to produce a model of paths,
Mm-hmm.
and this model is sort of combinatorial.
Exactly.
And that's what you call code.
Right.
Yeah, but in other cases, it's not quite as combinatorial. So like when you do pi n of Sn, then like the codes for Sn plus 1 is the previous sphere. So like, I mean, it's like not always like a number or something.
It's a little more combinatorial than what you started with, maybe.
It's, like, it's whatever you think those paths are supposed
But
to
it's a
turn
model.
Yeah.
It's a kind of
Yeah.
model that
Yeah.
you take
Mhm.
somewhere.
Right.
Yeah.
Okay. That's the secret of everything.
Including gluing. Okay, so what we have a category C, the syntactic category, which is defined by some universal property. It's an initial object, so we know how to map out of it the same way we knew how to map out of a higher inductive type. And we want to understand Hom1 nat. Right? That was what we wanted to understand what the closed terms of type nat are. So 1 is our base point x0, nat is y0, and the Hom set of a category is like the space of paths in a higher inductive type, or in a groupoid. So what we do, right, we can't say anything about nat, just like I said at the beginning, right, because the terms of type nat may involve other types, so we have to generalize to Hom from 1 into A for every A. And now we want to describe what Hom1A is in some more combinatorial way. So now we define codes from C to, well, in this case, this is to set, and decode says for all A and C, we have a map from codes of A into Hom1A. So these together are the functor R into the glued category, right? So we have a functor from C into set that gives us this object up here, R of C, and then we have this natural transformation that takes R of something to Hom1 of that same thing. So it's a little bit different than the simple version of this thing that I wrote up there, where in this case we're defining both R and this, both the code's fibration and the decode function by a joint induction. And I've been told that maybe this is also sometimes used for the higher inductive case, but maybe this is actually not true. Yeah, that's what he said.
So is this just a new terminology to describe the gluing construction?
Yeah.
Or this is a new idea?
Well, I don't think it's really a new idea. It's just pointing out that this gluing construction in logical relations is an instance of the same sort of idea, which we're also using to characterize path spaces.
Because it's Hom1 on one side, it's path.
Mm-hmm. It's directed paths in the category.
The encode is some kind of unit of lemma.
Mm-hmm. Exactly. Right, and then the encode is really just this thing here. Right, this well, we made this here actually. Right, that given an actual path, we encode it to get something in R of A by applying this sort of functorial action or composing with the image R of the point, R of that morphism. So in this case, it turns out that these two are not, in general, both identities. So just like we said, this thing is a surjection, but not, in general, an isomorphism. So we get this one is an identity. So encoding picks out, is like it's a section of the decoding. But in general, this one might not be.
So do you mean that one may possibly use logic in homotopy theory, so to speak? Because this is suggesting that, no? That you may use logical inference.
I mean, in a sense, that's what we've been doing all year.
Yes.
OK, so that's all I wanted to say about gluing. Any other questions or comments? Gluing in general, I mean. Yep.
So this terminology, code and code, code and decode, it's also used in normalization by evaluation.
Mm-hmm.
Ulrichberger and Schwistenberg, but there, so the goal was to build an inverse of the evaluation function. So your code from C to set, it looks like the evaluation set, theoretic evaluation. That will be in what they were doing. That was this situation. So you have the semantics, set theoretic semantics. You want to build an inverse to this map.
OK.
But then code is semantics, and decode is coding.
OK.
So
So, so there's a level shift that sort of happened. And, you know, it's not quite the same meaning of the words. OK. Yeah. OK. Let's see. So what about homotopy canonicity? So we have this problem in homotopy type theory, right? That there are some things that we'd like to be true, and we don't fully understand how to make them work as rules in the type theory. Things like univalence axiom or function extensionality, or maybe some things about higher inductives that we don't know how to formulate correctly. So what we can do is we can express them as axioms in the type theory, where we just say there's some term that has this type, and I don't know anything about it except that it's there. I've just thrown it in, and then I can do other stuff with it. And that's great because at least it gives us these facts, but it sort of breaks this ordinary sort of canonicity, because then we can write down particular terms of type nat or bool which use these axioms, and then the reduction algorithm doesn't know how to deal with those axioms, so it can't actually compute them out to get in something which is equal to a numeral in the definitional or judgmental sense of equals to. So one way to deal with that is to improve the type theory so that it incorporates these things as more computational rules. And Dan Licata and Bob Harper showed how to do that in some one-dimensional truncated case. And Dan and Guillaume are working on some infinite dimensional case right now. A different approach would be to try to prove some weaker statement, like where we replace equals to by homotopic to. So when Vladimir introduced the univalence axiom, he conjectured that this would actually be true. So let me write this up. Conjecture, given some number of univalent universes, by which I mean universes together with axioms asserting that they are univalent, so axiomatic univalent universes. Every closed term of type nat is propositionally equal to a numera. And you might ask for also for an algorithm which would give you, which given such a term, would compute the external natural number n and some propositional equality term exhibiting that equality.
Can't you prove this with your method?
So this method is going to, I claim, give a partial proof of this conjecture. And the problem has to do with not having a good external fully homotopical thing to glue with. So I'll sort of explain where that comes in. Yeah, we need to deal with the global sections functor, right? So we're going to do some sort of gluing. And if we sort of in a beautiful world where we had good notions of infinity one category and structured infinity one category, and we knew all of these facts about structured infinity one categories, then we could do the same sort of thing with sort of a homotopy global sections functor. So we could consider this global sections functor, which sends a type to the space or the infinity groupoid of global sections, of maps from the terminal object into that thing. And then we could do exactly the same sort of gluing construction. We would have a glued infinity one category, which would project down to C, and then we'd have a section, and this would be homotopic to the identity because this would be an initial object in some infinity one categorical sense. And then the infinity functoriality of this would give us this sort of thing, and that diagram would commute up to isomorphism, up to equivalence, and then that would give us that everything was homotopic to a numeral. But unfortunately, we don't have this yet. So we have a notion. We have notions of infinity one category, but we don't have a good. We don't really have as a theorem that the syntactic category is initial in the world of infinity one categories in any useful sense. So this would be a great theorem if we had it, and it would let us do this here. But what we do have is we have this corresponding theorem for the sort of the homotopical models. So what we do have that the syntactic category is initial in a one category, just like before, of some homotopical categories of some sort. So there are different ways that you could formulate whatever this sort of structure is. It's not quite a model category, but it's got some sort of vibrational structure and so on. Basically, it's a contextual category. It's the thing that we saw in the case of dependent type theory with the notions of dependent types and families and so on. But it's got sort of structure which models the identity types, and from that we can build a homotopy theory. So what we'd like, so can we find a model for infinity groupoids which is of this sort and a functor H. So the answer to this part of the question is yes, that's what the simplicial set model is. So Vladimir's simplicial set model is a model for infinity groupoids, and the proof is essentially that it does live in this category. That's how we get this semantics in that univalent model. But I have no idea how to define a functor H which lands in the simplicial set model. You can define some sort of pseudo functor, right? Because you want to send a type to some simplicial set or semi-simplicial set of types and higher identity types, but we only know how to define this functorial action by using id elimination, and those things don't end up being strictly functorial. So we don't know how to do that. But what we well, yeah, well, that's a secondary problem, right? it would be nice to have the theorem be true, even if we didn't have an algorithm for it yet. So what can we do? Well, what models do we have which sort of act like an external world? So we have sets, which is sort of not a very interesting homotopical model because it doesn't have very much homotopy, but it does have one univalent universe. Namely 2. The universe of propositions is univalent in set, the subobject classifier. And we also have groupoids, one groupoids, which has 2 univalent universes. 2 and set, right? The groupoid of small sets is another univalent universe. And moreover, the set of natural numbers belongs to this second univalent universe. So can we glue with these models? Well, so what is the global sections functor? What can the global sections functor be? Well, what we want to get out is a propositional equality, a homotopy. So we have the ordinary global sections functor landing in sets, but something is going to go wrong if we try to glue with that, because that would be giving us, if it did all work, that would give us actual judgmental equality, and we know we can't have that. But what we could consider instead is a functor to set which takes the quotient of this global sections functor. So the morphisms from 1 to A modulo homotopy. Yeah. Right. So if you regard the Hom as a space, then you take pi 0 of it. So in other words, this is, I say, P is T is equal to T prime if there exists a closed term proving their propositional equality. Exactly. This will not be left exact, right? So this is a problem. Right. So this is not left exact unless all types are H sets. If all types are H sets, then this is left exact. And in this case, it works. It's more or less the case we already know. It gives us one univalent universe of propositions. So I don't know whether or not this is already known, that univalence for propositions. Yeah.
What's the result exactly?
Okay. So this is if you have with all types being H sets and one univalent universe. What? More or less, yeah. I mean, yeah. It doesn't have to classify all the propositions necessarily, but it's sort of like the subobject classifier. Yeah. Yeah, I guess this really is just the case of a topos, isn't it? Yeah?
It's a little weird because when you say all types are H sets, you're adding an axiom.
You're adding an axiom, right?
So it should make things harder, not easier.
Well, it makes things both easier and harder, right? So it makes things harder because you have more terms that you need to prove are equal to numerals, but it makes things easier because you have more. It makes it easier to build the equality, connecting those terms to numerals.
I have a question.
Yeah?
So yesterday, I think you and theory showed that it was not, or conjecture that it was not necessary.
I'm going to get there. Yeah?
Okay.
is homotopic to a numeral.
So
That's
theorem of
is topos theory. Okay.
The
Free topos.
elementary topos.
And I guess that you can prove that in the same sort of classical gluing sense, right?
The original theorem of Drive.
Right. Right. Okay. Thanks for formulating that way.
It means that even if we had this principle of propositional externality, means that any two propositions which are pure and vertically equivalent, so that we don't destroy, propositional probability, canonicity for
Right. But then that's what Andre was saying, is that we knew that already because of elementary topos theory.
this is the topos. This is something we can
Yeah, but that's something weaker. So, I mean, in some sense, like the stronger theory also applies to the weaker case, right? Well,
I mean,
It-
will
it-
there be sort of similar or analogous results for algebraic set theory, for sort of weaker set theories for intuitions?
yeah, I guess.
The one corresponding to H, whichever one.
Okay, so maybe it's a little weaker than elementary topos theory. Jared, did you have a question, comment?
You cannot function extensionality.
Yeah,
Yeah.
function extensionality you need to.
Do you need to say that the universe contains only H props?
I don't think so.
Like, can you positively put nat into that universe?
No.
That wouldn't make sense. Okay.
Because if you right, so you can't take something like nat and put it into the universe, because then the universe would not be an H set.
Right. Okay.
But I don't think that you need to explicitly assume that every type in the universe is a prop. What?
I don't think it's true. You can bigger universes, which are still H sets.
Yeah, so I just said you can't put nat into the universe, because nat has an automorphism which is not the identity. So if the universe is univalent, then it's not an H set if it contains nat.
Once you've added the axiom that all types are H sets, that then implies a lot about what can and can't be in the universe.
Right,
But it's not clear whether you have to add anything more beyond what that already implies.
right. Right, in theory, there might be a type which is not an H prop, but which nevertheless has no non-identity automorphisms.
Hang on, but you thought about this universe itself.
Mhm.
It's univalent, right?
Yeah, the universe is univalent. That means that the identity type of the universe between two types in the universe is equivalent to the type of equivalences between those types. So if I have any type in the universe which has a non-identity automorphism, then the universe will contain non-identity paths but from a type to itself, and so not be an H set. Okay? Okay, so that's what happens if we try to glue with set. We can do better by gluing with groupoid. So if we do all of this in the corresponding way to gluing with groupoid, where we take A to B now, we take H of A is a groupoid with objects, the closed terms, or the global sections of A, literally, not quotiented by anything, the set of these things. And then the morphisms from T to T prime are proofs of propositional equality between T and T prime modulo the relation of propositional equality between those proofs. So this is the same thing sort of one level up, where we take pi 1, the fundamental groupoid of this space of closed terms. And for the same reasons, this is not left exact unless all types are 1 types. So one level up from H sets, but in that case, it is left exact. So if all types are 1 types, and we have function extensionality and 2 univalent universes, say omega and u, and now we can assume that the natural numbers type belongs to the second universe u, then we get the same thing. Every term of type nat is homotopic to a numeral. So now we can have this second universe can be univalent and still contain the natural numbers object, because then that only makes it into a 1 type. Rather, it doesn't have to be a set anymore.
In this case, U is like the group area of all small sets.
Right. Yeah. U is like this. Right. So basically, we need to glue together 2 things that have roughly the same structure. If we have this type theory with all H sets and 1 univalent universe, we can glue it with set, which has 1 univalent universe. We have this type with all types groupoids and 2 univalent universes, one of them containing nat. We can glue it with groupoids that has these same properties.
So I'm a bit confused. Are you saying that this functor now is preserving finite homotopy limits, so to speak?
Yes. So if we assume that all types are 1 types. So that means that any 2 parallel any 2 parallel 2 morphisms are equal.
It's like a
Right.
universe of groupoids, so to speak.
Yeah.
I see. It's because
But it doesn't preserve any, it doesn't preserve limits, it preserves only homotopy limits.
Right.
So one also needs some sort of a generalization of the initiality theorem for the at least one-dimensional homotopy.
Well, no. What it preserves homotopy limits, but it also preserves strict pullbacks of fibrations, which are particular homotopy limits, but it actually preserves them up to isomorphism rather than just up to equivalence, and that's enough for the ordinary initiality theorem to apply, I think. Because the reason it preserves them up to, strict pullbacks of fibrations are homotopy limits, so it preserves them up to equivalence, but it actually preserves them up to isomorphism because the set of objects is literally the set of closed terms, and that is the ordinary global sections functor, which does preserve limits on the nose, up to isomorphism.